everyone. Welcome to the webinar Medical Device Testing Simplified, the MedTEST system, brought to you by Medical Design and Outsourcing and Iconics. Just a couple of housekeeping details before we get started. You will see several boxes on your desktop, all of which can be moved around to suit your preferences. You can enter your questions in the Q&A box, and they will be addressed after the presentation. Another box to note is the additional resources box. This box has websites and other information on this subject. We would like to thank our presenters for being here today, Anthony Arroyo, Applications Engineer at Iconics, and Carl Gerberick, International Business Development Specialist at Iconics. I'm Danielle Kirsch, Senior Editor of our Life Sciences brands, and I'll be your moderator for today. Without further ado, I will hand the presentation over to our presenters.
Great. Thank you, Danielle, and welcome everybody to our MedTEST webinar. My name is Carl. I'm with our International Business Development Group, and I'll be joined today by my colleague Anthony Arroyo from our Applications Engineering team. And as we get started, let me share with you a brief outline of what we'll cover today. I'll begin by describing a bit about MedTEST, how it came to be, backgrounder, and highlight some of the key benefits. And then since we're joined by a number of our international sales reps on this call, I'll also talk briefly about MedTEST from a sales perspective. I'll then close out my section about how you can engage with Iconics in working together to get started with your MedTEST application or opportunity. And I'll also highlight some of our consulting services. I'll then turn it over to Tony, who's going to first talk about electrical safety tests for 60601 as it relates to MedTEST, and then he'll dive deeply into leakage current test types. And then we'll close out the webinar with a Q&A session, and we really encourage you to log your questions as we go along. So first, a history of MedTEST. So how did MedTEST come to be? It started several years ago when a major laser surgery device manufacturer approached the industry and challenged us to reduce DUT test time and decrease operator intervention during testing. And this is not an issue unique to this specific manufacturer, but was really a broad-based issue that everybody in the industry was experiencing. And there were really two main pain points to overcome. The first is existing line leakage testers were prompting the DUT to power down between test steps. And this is somewhat similar to the way that your PC or your laptop might go to sleep when you're not using it and the delay you experience in starting it up again. And this power cycling between steps added significantly to the overall test time. The second pain point was one of cable management. Changing multiple cable connections during test steps proved difficult for even most experienced operators to efficiently manage. And these technical challenges were not easy to overcome, and in and of themselves, it prevented a number of our competitors from developing an offering. So these pain points led us to introduce our MedTEST solution. And here I'd like to highlight three of the probably the most important benefits of the system. First, it's a complete all-in-one solution that combines the commonly required safety tests into a single integrated system. And it does so on a very compact platform that's designed to fit into a standard rack mount to reduce space. Then secondly, it includes something that we call Active Link. And this patented feature allows the DUT to run continuously without shutting down between line leakage tests, and really addresses that pain point I described on the previous slide about power cycling between test steps. And all of this significantly reduces test time and eliminates operator intervention. And then the third key benefit is fully automated sequential testing. A typical test scenario will feature a minimum of 8 steps per patient lead, but most tests feature multiple patient leads that then become a challenge to manage manually. MedTEST, combined with a series of scanners very similar to the one that you see pictured in the upper right, can perform multi-point sequential testing without the need to change test leads. The scanners are in conjunction with the instruments are then controlled by software for a completely automated setup. Now, these next couple of slides are really intended for our international sales rep audience, so I'll go through those quickly. But for those reps that are in the audience, I'll follow up with some additional information to really amplify on what I'll talk about here. So first, know that there's limited direct competition. This is an application that Iconics effectively owns. We're the #1 solution provider for this in the US. And in terms of the sale opportunity, each MedTest system includes an Omnia instrument, at least a pair of scanners, and an AC power source. So there's a high dollar value associated with this. Initial orders often generate repeat orders, so there's a high rate of customer adoption. And similarly, our unique differentiators make it difficult for our competitors to displace MedTest, so there's a very high rate of customer retention associated with it as well. Next, MedTest customers are typically very solution-driven and less price-sensitive. And what do we mean by that? Well, everybody works within their budget constraints, but MedTest customers in general are very value-driven, very ROI-driven. So if we can prove out the benefits of our solution, these customers are typically more willing to pay for that. And then apart from the medical device field, MedTest is a very versatile system, and it's not just for medical device manufacturers. We found that appliance manufacturers are also a key target for line leakage testing. Our Omnia 2 instrument, for example, in conjunction with our leakage current tester, 620L, can provide up to 40 amps of continuous current capability for testing applications that are pretty common among appliance manufacturers. And lastly, as I close out my section, let me talk a little bit about working together. We encourage everybody, our international reps and our prospective customers alike, to engage Iconics, leverage our experience and expertise before and after you commit to the sale. For our international reps out there, we encourage you to contact medical device customers in your market and ask them, what test systems are they using today for 60601? Are they satisfied with that existing system? Describe to them some of the MedTest benefits that I'm highlighting here and that Tony's going to go into in detail, and ask them if they would consider an alternative. And if they would, don't feel that you have to go at this alone. Offer to schedule a technical call with Iconics so that you can take full advantage of our experience in trying to help bring the customer to see the value of the MedTest solution. And lastly, I want to touch on our applications consulting services. These services are really unique in the industry, and we encourage everybody in this audience to take full advantage of that. We offer a range of customizable packages that can help everybody overcome the challenges associated with testing and minimize the risks. And these can begin from digital packages that can help establish best practices for operator safety in operator electrical safety testing, to on-site training that could be customized for your specific application or your specific testing environment. Or it could be on-site validation, especially for more complex applications where you really want to have a very smooth installation and startup experience. So those are some of the consulting services that we offer. We encourage everybody to visit our webpage to learn more about both our consulting services and our webpage on MedTest Solutions. So with this, I will turn it over to my colleague, Tony, who's going to go into this in more depth. So thank you.
All right, thanks, Carl. Just to confirm, you can hear me, right? Just want to make sure my audio is good.
Yep, loud and clear.
Perfect. Okay, well, thank you for that valuable information. Now we want to get into a little bit more of the technical side, talk about the electrical safety test that we find within IEC 60601-1, third edition, talk about the actual concepts of what's happening, and then look at our MedTest system, which allows you to run them all sequentially in an automated fashion. So these are the popular tests ran: ground continuity, which is a simple check to make sure there's a continuous path on your protective earth circuit. Ground bond is a similar test, but now we're injecting high current. We want to stress that circuit. Will it heat up? Will the resistance increase? 60601 allows you to test an AC and DC. This is, of course, our HIPOT test, where we're verifying the integrity of different insulations on your product. And then leakage testing, which is probably the most intricate and it's kind of the toughest to understand how to set up. And so that's why we kind of developed our MedTest to simplify it. And we're going to get into all these topics in the next few slides. So let's begin with the ground bound test. The ground bound test verifies the integrity of the ground connection by injecting high current into the ground pin of the product's power cord, which flows through the chassis and is returned on an accessible grounded part. Okay, so this determines if the safety ground wire is capable of handling excessive current flow in case a fault occurs and the product's insulation fails. So we want our ground circuit to always be the path of least resistance, especially in the medical field, right? Where we might be physically connected to the human body, right? If there's any leakage occurring on our chassis, we want to make sure the ground circuit is always going to be where current chooses to flow. And if we look specifically into what IEC/UL 60601-1 says about impedance and current carrying capability, otherwise known as the AC ground bond test, your requirement is a current of 25 amps or 1.5 times the highest rated current, whichever is greater, plus or minus 10%, pass through the protective earthing circuit. Frequency equals 50 to 60 hertz. No load voltage should be less than or equal to 6 volts. And so that means the voltage driving the current, right? We want it to be less than 6 volts. And our Omnia analyzer, Omnia 2, I should say, allows you to set that between a 3 to 8 volt range to help you meet those standards. We also allow you to choose between 50 or 60 hertz to make sure you're meeting all those requirements. Now, what's the pass criteria? What do I look for to pass this test? Impedance protective earthing circuit on the DUT should be less than 100 milliohms. And for DUTs with non-detachable supply cords, we want to make sure we're less than 200 milliohms. Okay, and so let's actually bring in what we call our MedTest system. And so before I specifically talk about what's happening with the ground bond test, let's look at this iteration of a MedTest. Again, this is one version of a MedTest system. You can design it or choose your components to fit your testing needs. Up top here, we have our Omnia 2 8207. This is our actual electrical safety analyzer. It can run ground bond, HIPOT, and leakage current, all the tests that we're going to be discussing today. And here, let me get a pen here, but if we look here, this is called our leakage module. This is where you can attach our adapter box, plug your DUT in, and run ground bond, HIPOT, and earth leakage from the same connection points. You don't need your operators to change connections. You can run all the tests sequentially, get your results, and never worry about operator error. Okay, that's the beautiful thing about that LLT module. Now, on our right here, we have the DUT, right? Let me clear some of this, but our DUT, you can see we have applied parts being sent to a scanner. Our scanner, we call this our main scanner. This allows you to run the other type of leakage test, patient leakage, right? I need to test leakage from an applied part to mains. Well, what I can do is take all my applied parts, send them to a scanner, send one side of the MD to that same scanner, and I'll short those. Now, maybe I'm using terms right now that I haven't discussed and we're going to get to later, but I just want to kind of explain what each component is doing in this MedTest system. Similarly, this is what we call a secondary scanner. Our main scanner can control the secondary, and now we can send, let's say, the other side of the measuring device to the second scanner. And here is our, what we call a T2. For certain tests like mains and applied part, which again, we're going to get to later, you need to short the line of a second transformer, a T2, to the other side of the MD. And this gives us that possibility. But let's get back to the ground bond test. We're talking about the ground bond test, and we want to understand how that works with our MedTEST system. Here on the back, we have what we call our GND port. Okay, these connections here will be attached to an adapter box, which your DUT will be plugged into. And during the ground bond test, current is injected into the ground pin, right? That current flows through the entire ground circuit of your DUT, returning on the chassis point, which is connected to our case lead. And so this completes a loop that allows us to measure the resistance in your ground circuit when 25 amps is applied. Will that impedance, will that resistance stay within that 200 milliohm limit? Another great thing about the Omni is we have an offset feature, meaning it's not fair to you to count the resistance in our adapter box, in our case lead, and have that count against your DUT. So we allow you to offset that resistance to make sure you're getting a true value of your ground circuit's resistance. All right, so that's the ground bond test. That's how it's performed in this iteration of the MedTEST system. And now next, I want to talk about the HIPOT test, but I'm going to be using this term leakage current, and it can mean two different things. So let's discuss those differences first. Touch current, that is when I'm referring to a leakage current test. Okay, that is measured when the device is powered up during various operation states. So we are looking to simulate scenarios within, a hospital or anywhere where your medical device will be in use. I want to know when this is powered at 110% of its rated voltage and certain fault conditions occur, whether it be a power outage, an electrician reversed the polarity on an outlet, right? What type of leakage will I be seeing to the ground circuit, to the chassis, to certain applied parts? That is what this leakage current means, okay? What that touch current, what leakage current test step, we're referring to that. And IEC 60990 second edition gives you direction or methods on measurement of touch current and protective conductor current. And so that's where you would reference to understand how to run these tests. And we've used those requirements to design our Omnia to make sure we're running it in the correct fashion. Okay, now HIPOT leakage current is completely different, right? We're not just powering on a unit and seeing how our design is working. Instead, we are overstressing insulation with high voltage and looking for weak points in the insulation to see if we can force current through. Okay, so a HIPOT test measures leakage through product insulation while the device is powered off. Insulation is stressed by high voltage and the resulting leakage current is measured. Okay, and here you're allotted a little bit higher limits because we just want to make sure there's no shorts. There's no way for mains to come into contact with your ground circuit, putting operators or patients in danger. And so once you verified your ground circuit with your ground bond test and now performing your dielectric test, you have peace of mind that your two methods of defense to protect your customers or your patients are safe. So the dielectric withstand test, also referred to as a HIPOT test, as I said before, it's used to determine whether the insulation of a product is able to withstand an over voltage condition. This test verifies that the insulation of a product is capable of protecting the user from any leakage currents as a result of an electrical fault within the product. So looking specifically into the standard, as I mentioned earlier, alternatively, a DC test voltage equal to the peak value of the AC test voltage may be used. So if you find yourself with a product that has some unintended capacitive coupling where running an AC test might give you some false failures, you're allowed to run a DC test using that peak voltage of the AC requirement. Now, the second part B is really important. During the test, breakdown constitutes a failure, okay? So what is the definition of breakdown? Insulation breakdown is considered to have occurred when the current which flows as a result of the application of the test voltage rapidly increases in an uncontrolled manner. That is, the insulation does not restrict the flow of the current. Corona discharge or single momentary flashovers like arcs is not regarded as insulation breakdown. All right. So Associated Research sells a variety of different hypot testers with different capabilities, right? Some, when performing hypot, can allow you to leak up to 20 milliamps, 40 milliamps. We even have some testers that can leak up to 99.99 milliamps. And I bring that up because we've defined breakdown as your product is trying to draw more current than our internal transformer has the capability to. And so at that point, we need to protect our internal hardware, and we call that a breakdown. Okay. Now, if your product is consistently leaking 10 milliamps, sure, that's something to look into, but that would not be rapidly increasing current in an uncontrolled manner. And so that would still be considered a pass. Okay. So I just wanted to bring the point up that sometimes when you have a capacitive DUT, and you're constantly failing, you just might have the wrong equipment. Okay. Maybe you just have a capacitive product that leaks a lot of reactive current. And so you might need to use our 100 milliamp units. All right. So that, let me actually, so a test voltage for the working voltage to which the insulation is subjected is greater than or equal to the value specified in table 6. So a lot of our customers say, I bought your equipment, but I still don't know what parameters to set. All right. And we have to say, like, we aren't the governing body of your product. You need to reference the standard that you're testing to. And these standards, like we just showed, will tell you what the failure conditions are, but they will also tell you, what your parameters should be, right? Reference your peak working voltage. And from there, right? What are your means of protection? Is it 1 or 2? Well, then I know to test at 1500 or 3000. And then from there, right, is AC right for me? Is DC better because I have a capacitive product? And so it's important to, especially for our reps, right? Well, a lot of them will email you and say, like, what test voltage should I use? What high limit do I use? We can give them, recommendations on what we understand is industry standards or industry norms, but the responsibility is on them to find out, what standard are you testing to? You need to identify at what test voltage you'll need, what type of current you'll need, so that we can diagnose the correct unit for them. All right. I'm sure Carl can attest to selling a unit to a customer and then realizing it's not the right fit. So now we got to figure out, returning and exchanging and stuff like that. So it's important to make sure the customer has all the information before you come to Carl or before you come to the apps team, so that we can correctly diagnose their needs. All right. Now, how does the hypot test work on our MedTEST system? If you recall, I said these connections here, line, neutral, case, and GND are all coming, line, neutral, and GND are coming from an adapter box, while case is an alligator clip or a connection going straight to the chassis. What's great about the Omnia is it can short internally line and neutral. So now these points are shorted, right, to the high side of voltage. Our case lead here becomes the low side of voltage. So now we have the low side of voltage. Whoa, sorry about that. Well, the low side of voltage on the chassis. And what are we doing? Without making any change in our connections, we're performing the hypot test between mains and chassis, or mains and our ground circuit. And As long as we don't see a breakdown, that's considered a pass. So now you've just ran your ground bond test and your hypot test by just being plugged into our adapter box. That's kind of the beauty of the LLT module. All right. And so here, that was covering the ground bond test and the hypot test, right? It's not specifically restricted to medical device testing. Those are the most common electrical safety tests. Now we're going to get into leakage current testing, which some of them are very industry specific to medical. But let me bring in Bashan. Bashan, before we move on, are there any points you'd like to emphasize, or if anything I missed before we move on to some of the leakage current tests?
No, I think you covered everything pretty well. I just want to make a point that a system can also be set up. We've seen customers have 4 different ground bond points that they want to test. So a MedTEST system can also have multi-point scanners that perform multi-ground bond tests for you. So a system can, run through 4 different ground bond points, run your ground bond test, and then move on to a hypot test, and then the test you're going to cover next, which are leakage current tests. So I've seen some customers with established products that press a switch of a button, and they run a 45 minute test that fully tests their medical device for all the requirements they need.
Yeah, that's a great point. So a lot of your medical devices do have different grounding circuits. And so this red line here can be another what we call a GND module, or a ground module, which would be 8 ports that look like our GND port here, but now you can make those 4 connections to a respective GND port and then run those tests sequentially without having to change your connection. So that's a great point to bring up. All right, let's move on to our leakage current test and kind of define what that is. The leakage current tests are performed on medical devices to measure the leakage current, which could flow through a person while the product is operating. A measuring device, which we'll refer to as an MD, is used to simulate the impedance of the human body under different conditions, depending on the application of the product. The test is ran under both normal and single fault conditions and reverse polarity on the input line power at 110% of its rated voltage. So we're going to discuss what single fault conditions, but it's important to note that you shouldn't be using wall power to power on your DUTs when performing these tests, right? You need a dedicated AC source, like our EEC brand can provide for you, right? The standard says you must test at 110% of its rated voltage. You cannot get 110% from a wall outlet. Hence, you should be testing at 132 or 264, right? Depending if your input power is 120 and 240. So for our reps, if you're dealing with a customer who's ordering an Omnia and you know they're running leakage current tests, you want to make sure they reference their standard to say, are you sure you're not supposed to be running these tests at 110% of its rated voltage? If so, you may need a dedicated EEC power source or the internal source in the Omnia, right? Which again is another convenient feature of the Omnia. So let's talk about what those fault conditions were and how this test is measured. So leakage current is measured through a human body impedance network, also known as a measuring device. And so each standard gives you what the measuring circuit should look like. Okay, it's a very simple RC circuit meant to simulate the type of impedance our human body has. And what's great about the Omnia is we've already built those into the Omnia. Therefore, you can just select it on a parameter and set it and forget it. I guess we're gonna place that specific MD between the 2 points that we want to measure leakage, and we have some of the most common MDs used in the industry built in. So that's a big convenience of the Omnia 2 tester. So normal and single fault conditions. Let's discuss that here. So your test should be taken under normal conditions as well as a combination of all these fault conditions. And this is actually a simplified version of the diagram that you'll see in the 60601 standard, okay? What we have is our S1 switch, okay? when that is opened up, well, let's describe what's happening here. Here is our mains input, line and neutral. This is our DUT on the right, which is plugged into the adapter box, and now voltage is being fed to our DUT, and it's power at 110% ideally, right? And current is flowing back to the source. Now, what happens when you open the S1 switch? Well, I'm opening the neutral, and so I expect my DUT to power off. All right, and so that S1 switch is there to simulate a power outage in a hospital. If I'm in a hospital bed with multiple medical devices connected to me and there's a power outage, will that fault increase the leakage my human body sees? The next S2 switch, where I would connect this to this and this to this, well, I've just reversed my neutral and my line, right? So that's simulating me in a hospital bed, and someone's about to plug in a medical device, or someone has plugged in a medical device to the wall outlet where the electrician accidentally reversed the polarity, right? Will that fault increase the leakage that I experience? And lastly, if there is leakage occurring, which our ground circuit is meant for, right? What happens if there's an issue with the ground circuit? So our ground circuit is now open or gone. What type of leakage will the human body see? Okay, so those are the 3 fault conditions, which again, we've already built into the Omnia. You can say on or off, reverse polarity, on or off, neutral, open or closed, ground, open or closed. This is what we mean where, especially using our software, you can quickly make test files that will take into account all these different combinations. All right, and again, that was the biggest pain point of why I think Carl talked about it, like why we designed the MedTEST system, right? We had medical customers coming to us saying like, it's too confusing to try to keep track of all these steps and understanding if we're missing anything or doing this correctly. Leakage current tests, right? Let's talk about examples of different leakage current tests called out by the medical standard. And we've listed them below. The requirements for performing these leakage current tests depend on the type of medical device and the inclusion of applied parts in the medical device. All right, so touching on earth leakage. This is the most basic leakage test. I want to know when your product is powered on at 110% of its rated voltage with all those different fault conditions I've discussed, how much current is leaking from mains to earth ground, right? I'd expect it to be minimal because, again, we have insulation. We've run the hypot test to verify our insulation, but we still need to see, right, how much current is leaking, which we'll look at figure 13 and what that means. And so that can be ran without scanners, just your Omnia tester. Same with touch current. So now touch current is enclosure leakage. Not all enclosures are grounded chassis, right? And so the IEC board decided, well, we can't assume that everyone's design is some sort of grounded metal chassis. We need to identify what type of leakage is seen on all parts of the enclosure. If my hand comes into contact with this during those fault conditions, what type of current will I see? All right, and that's figure 14 in section 8.746, which we'll in the future slides, we're gonna look at those figures. Now, patient leakage general. If you have a medical device that doesn't have any patient connections, you can get by with just earth leakage, current, and touch current. But now when you bring in applied parts, a part that's going to be entering or connected to the human body, we now have to run this new set of tests. Patient lead to earth, figure 15, section 8.7.4.7a, right? How much is leaking from the actual patient lead to earth, right? Now we're not looking at mains to earth anymore. Now we want to know from the patient connection to earth. And that's where it begins to become convenient to use our scanners to make all these connections. Otherwise, you're relying on maybe not well-trained operators to perform these very intricate and important tests. Mains on applied part. We're going to have a whole section on this test a little bit later on as well, because this is probably the one that confuses our customers and reps, for that matter, the most, right? It's a very complicated system where, consider me the measuring device, right? I want to know how much leakage is going through me. Mains on applied part is simulating what happens when I have a normal medical device patient leakage connected to me, and a luminaire falls. So I somehow my other hand comes into contact with line voltage of a second transformer, a second power source, right? Ideally, I'm floating in a medical bed, but the fact that I'm connected to another medical device and now coming in contact with the line of a second T2 transformer, will that cause extra, what type of leakage will I feel? Okay, and that's mains and applied part. And we have created a system on how to perform that pretty seamlessly. Mains on signal IO, mains on SIP-SOP is sometimes called, very similar to mains and applied part, but instead of being connected from the line voltage of a T2 to an applied part, we're now being connected to the signal inputs of your medical device to see what type of leakage we see there. And then mains on non-protectively earthed chassis, right? Performing earth leakage and touch current, right? Will having mains on my non-conductive chassis change the value of those results? So depending on the design of your product, right, you may be forced to run a plethora of these different tests, and that's where the MedTEST system comes into play, making it automated and sequential. And like Prashant said, press test, and 40 minutes later, you've ran through all these different fault conditions, scenarios, and have your results. Patient auxiliary, patient lead to lead, right? You also want to know, right? Forget me coming into contact with the line. The fact that I'm connected to two different patient leads, right? Are they somehow affecting each other, causing leakage through the human body? And so those are pretty much the main leakage current tests that you'll need to perform according to our medical standard. And now let's delve deeper into each one specifically, so we have a greater understanding. Earth leakage. So I want to know, this young lady on the left, she's coming into contact with a device plugged into the power outlet that has a good ground. And so if there is leakage coming on the metal chassis of the toaster, well, yes, she is a path to earth that current may want to choose, but there's a good grounder. The ground circuit's there with less impedance, the path of least resistance, so it's going to choose ground. What happens? So how can we measure that value? How much do we know? How do we know how much is actually leaking to ground? Well, what we want to do is remove the ground and place the MD, or the human body, between your protectively earth chassis and ground. And we can measure now how much earth leakage is occurring. And so this diagram up here is taken directly from the standard. And if we look here, this is our T1, right? That's either the source inside the Omnia or an EEC source that you're routing through the Omnia. But for all intents and purposes, it's what's powering on your DUT. And so, right, this power is coming. Let me select the pen here. Right, power is coming into your DUT and ideally flowing back out to its source, right? Now, what happens when current starts leaking onto the protectively earth chassis? Well, it's going to take earth. We've placed our MD, our measuring device, the circuit intended to simulate the human body, and that current is going to flow through the MD where we can measure it and return back to the source. And you can see that in the diagram, they call out the S1 switch we referred to, right? Neutral, open, and close. The S5 switch, reversing of the polarity. And there's no need for a ground open or close because we've placed the MD directly on the ground circuit. So you will be measuring earth leakage. Now, there's a functional earth. So it's saying, hey, if your product is designed with a functional earth, open and close that. So give me those combinations as well. All right, and so that's earth leakage. We always look where the MD is placed within the diagram. I can see the MD is placed between the protective earth and mains, so I know that's earth leakage. All right. Now to perform that on the Omnia, we would do a probe configuration of ground to line, which is why we call it protective conductor current. All right. You can see the MD is between earth and mains. Here we can open and close our neutral or reverse polarity, and we want to keep the ground circuit open, right? Because if we keep that ground closed, we're shorting out the MD, and we're gonna see our leakage be 0 microamps. All right, so that is earth leakage. Let's talk about touch current, enclosure leakage, which some kind of can confuse with earth leakage because it's kind of a similar setup. But remember, this is intended for the happenstance where the design does not have a grounded chassis, or not every accessible part on the product is grounded. And so I want to identify where on the product do I see the most leakage. Okay, so we look at the diagram again. What's changed? Where is the MD, right? So the MD is now here, no longer between protective earth and mains, right? It's not on the ground circuit. I'm connected directly to a touch point on the enclosure. So from a touch point to mains, how much leakage am I seeing? Therefore, to perform that on the Omnia, I now need to use a probe, right? So if you look at our MD here, one side is still connected to mains, right? The other side is now an accessible probe. And this is where it all fits together. I'm sending this probe high to a scanner channel, and I'm sending the enclosure point to a different scanner channel and shorting those, right, with our software. This way, operators don't need to be taking probe high directly to the DUT. No, because I might need that probe high later. So why am I going to commit it to one point? I can take it to a scanner and at different test steps, short it to different points. That's the beauty of the MedTEST system. Okay, so again, probe configuration, probe high to line, and we call that touch current. So one side of the MD via the probe is connected to an enclosure point, and the other side of the MD via internally the Omnia is on the mains of your T1 transformer. All right, that's enclosure leakage. Patient leakage. So again, always identify where is the MD in the circuit, where is the measuring device. To be a little bit more clear on what's happening here, if I didn't make it clear, right? Power's coming in, powering up the primary side of your medical device, right? Current's flowing back out. Obviously, the secondary side is our applied parts, right? These are the parts that are actually getting connected to patients, right? We want that insulated from mains input, okay? And then here we have a functional earth and your ground circuit, right? So it should be very understandable. And then our fault conditions. So in case that wasn't clear earlier. And so now, where is our MD located? Let's describe, this picture tells you, right? I just want to know when I connect a patient connection, which is intended to be on the human body, and I'm powered up at 110% of its rated voltage, and I simulate a power outage, and I simulate reverse polarity, what type of leakage may that patient see? And so to simulate that, we've now placed our, let me change my little pen here. We've now placed our MD between an applied part and still mains of our input. This is why I said take all your applied parts to a scanner channel, to scanner channels, right? If you have 3 applied parts, take them to 3 respective scanner channels. And now probe high is also sent to that scanner, right? Here's probe high. I'm just connecting that directly to a scanner channel on our main SC6540 scanners. And depending on what test step I'm on, I can now short channel 1, where my probe high is, to channel 2, where my first applied part is. And I've just ran patient leakage for 1 applied part. Hey, the next step in the Omnia test file, short channel 1, which is again my probe high, to channel 4, which is my applied part 2, right? This is all being done internally on the MedTEST system. So it alleviates any messy connecting, reconnecting, connecting wrong, and saves a lot of time. And so to be clear, to emphasize what patient leakage is, we look at where the MD is placed on the diagram, which is between mains and the various applied parts. We apply 110% of rated voltage, perform all the fault conditions, and figure out how much leakage we're seeing. And are we staying under limits called out in tables on inside our IEC 60601-1 standard. And so let's identify how that happens in the MedTEST system. Okay, so earth leakage. If you recall, I said our adapter box, right, which connects to line, neutral, and G&D, your DUT's input cable is plugged into our adapter box. So now we have access to your mains, and we also have access to your grounded chassis via this case connection, okay? And so it's almost like there's no connections to show because it's all done internally on the Omnia, right? I have mains coming through here, which is accessible internally on the Omnia, right? I'm connected to the chassis via the case. And so now all I got to do is supply 110% of its rated voltage, perform all the fault conditions, and internally, the Omnia can place the MD between mains and chassis. And now we're measuring earth leakage. Okay, so as I stated previously, you can run earth leakage without any of your scanners, right? The most widely used electrical safety tests for medical devices, which are ground bond, high pot, and earth leakage, you just need, your 8207 and you're fine. Now, so that's earth leakage, right? All done via the adapter box. Now, the next test, if I can remind you guys really quick, was enclosure leakage. We're missing an E here. So enclosure leakage. So where is the MD? Between an accessible enclosure point and mains, right? So we go back, an accessible enclosure point and mains. And so what you can do is I would take this point on the chassis, bring it to this scanner channel. And if we go back, right, my probe high needs to go somewhere. My probe high needs to somehow come into contact with this point here, right? The other side of my MD, again, it's still internally on the Omnia connected to mains. And so we make that connection again. We come here. We're sending probe high to that same scanner. So now I can say, all right, for my next leakage step, perform channel 1 and channel 4 high, meaning they're shorted together. my probe configuration of the leakage step is probe high to line. And so now that means it's going to be measuring from probe high, which is connected here, which is shorted to this channel, which that channel is on an enclosure point. So I'm measuring leakage from this enclosure point to what's the other side of the MD? Well, mains of your DUT input, which I have internally on the Omnia. And so that's how we use our probe high and our scanners to test for enclosure leakage. All right, let's see. Okay, so we're about to jump into, no, actually, patient leakage, right? These applied parts, literally the same thing I just discussed. I've sent an applied part to a scanner channel. I have my probe high to that same scanner. All right, short channels make both channel 1 and 7 high. And now I'm testing probe high to line. Probe high happens to be connected to my applied part. I'm doing patient leakage. That's the beauty of the scanners and sending all your test point to a specific scanner, sending your probe high to that same scanner, and just editing parameters on your DUT. All right, so we discussed earth leakage, enclosure leakage, and now patient leakage. Before we go on to MOAP, or mains and applied part, Bashan, is there anything you'd like to add or may have missed there?
I think you covered pretty much everything. One thing I like to point out about the MedTest system and the beauty of it is that many people in the audience may have heard about what's called a reinforced hypot test. So typically a reinforced hypot test is a 4,000 volt test. The thing about the MedTest system is that it could run a 4,000 volt hypot test on your applied part, and then also run a leakage current test to the same applied part. So that's the reason we're using these scanning matrices or scanners, is that it's able to do multi-functionality. When it needs to do a hypot test, you're able to do that. And when it comes to leakage current test, you're able to route the current to the proper places.
That's a great point. So mains and applied part hypot, no wait, I'm sorry. Applied part hypot test, right? I have my high voltage sent to my scanner. And so that means I can apply high voltage to any of these applied parts and return on chassis or return on mains. That's what Bashan was referring to. Is like, hey, not only can you send probe high for leakage current to your applied parts, you can also send high voltage to that applied part, which are usually like those 4,000 volt tests, because you need to ensure that the insulation on applied part is much more rigorous than mains to ground. And so that's a great point to add, Bashan, right? You can perform applied part hypot with our MedTest system. All right, mains and applied part voltage. I keep discussing, right? Look where the MD is placed and go from there. So our MD is here. There's a lot going on here, right? This looks, I'm not sure if you guys can see my mouse. Let me point a pointer here. This is, we know what this is. We've just been looking at this. So now all we're saying is take one side of the MD to an applied part while still performing all these fault conditions, but the other side of the MD, take it to a T2. Let me choose a different option here, right? Our MD connected to an applied part, this whole area of the T1, right? We've just been discussing this at length. So we understand what this is. Perform the same fault conditions, 110% on T1 here, right? But now we're introducing a T2, a second transformer. I cannot use my Omnia's internal source for this because I'm using that as my T1, okay? That's why in our MedTest system, we bring in this second EEC source. So let me get back to the correct slide, right? And what you're doing is taking one side of the MD to the line of T2. How in the world do we do that, right? One side of the MD to the line of T2, the other side to an applied part, performing all the other fault conditions that we discussed earlier. What type of leakage do I see? And this is what I referred to earlier. I'm on a hospital bed, or I'm in some sort of floating state where I'm connected to a patient connection that's intended to be there, but now I've somehow accidentally came into line voltage from another source, right? What type of leakage will I see? And so this is the beauty of the MedTEST system, right? The second scanner I haven't brought in yet, right? But if you recall, the MD, let's pretend this is a human body with two arms. One side is coming into contact with the applied parts, the other side, the line of T2. So here, the MD falls between probe high and probe low here. Okay. And so we've discussed one side goes to this scanner with all the applied parts. So that's one side of the human body. One arm is touching the applied part. Now I'm taking probe low to the second scanner. And on that same scanner, I'm taking the line, the ground, and the neutral of my T2 to that secondary scanner. And from here, I can short probe low or channel 1 to line. And here I can short probe high to any of my applied parts I want to test. And now you're performing mains on applied part hypo. This is one of the most common iterations of the MedTEST system. And this is why you need two scanners, an extra EEC source, and the internal source on the Omnia. All right. So that was a lot of information to kind of retain and go over. I hope that it was clear. Obviously, these slides are available for you. If you feel like you need more information on these topics, as Carl said previously, our apps consulting, for all our international reps, like, we'd love to meet you. Please sell a consulting in your country, and we'd love to come out there and perform these consultings with you, provide extra training and just develop that relationship. If you want to contact Mara for any information on this webinar or get a copy of the recording, there is her information. She's great. Bashan, I know you've been kind of keeping pulse on the question lines. Are there any questions that you feel are worth sharing with the entire group?
Yeah, we have obviously our audience could ask questions, and Ben from the audience asked about any guideline for choosing the chassis point for ground bond test. So, I could answer this question for Ben, which I already did for the audience. Let me see if I could push this to. For a ground bond test, the standards recommends a metal accessible point on your product. Typically, this is a ground stud on your product. What we have seen customers use is also they use the screw, because a screw, an unpainted screw, is also a metal accessible point for a patient or an operator or an end user. So you want to make sure any point on your product that's accessible, that's metal, not painted with some non-conductive paint, you're supposed to test to that point as a ground point. And then we have questions about, there's an additional question about, for leakage current test, does the device need to be fully powered on? What if the unit takes 5 minutes to boot up? So I'll let you handle that question, Tony.
Yeah, that's actually a great question. And we see this occurring a lot because most products now are kind of soft button starts. And the standard says, in a steady state condition, right? It doesn't say take your leakage measurement in the 30 seconds of your boot up time. And so that's why our Omnias, we've established a delay time parameter where you can delay taking measurements of the leakage. We're still outputting current. We're still outputting input voltage, but you can now use that delay time to set your boot up time and kind of synchronize that so that when you're fully in your steady state, we'll go from delay time to dwell time, which is actually the test time, and make the appropriate measurement? So that's a good question. And yeah, we have accounted for that. I think that that kind of perfectly wraps us up. If there are any more questions, we're definitely going to kind of reach out to those individuals and make sure those are answered. I want to thank everyone for joining us, especially our reps. I know Carl is new, and I think he's an amazing asset to the company. And I really think that you guys are going to start getting you guys are going to get quality support. And we look forward to working with you guys and hopefully start quoting out more MedTest systems in the future. Carl,
Great.
would you like
Thank
to
you, Tony.
Yeah.
Yeah.
Okay, perfect. Well, thank you everyone for your time. If Danielle doesn't have anything, then
Yes.
actually I'll let Danielle wrap up.
Thank you, Anthony. Yeah, this was a really good presentation, and also thank you to Carl. That's, as I mentioned, that's all the time we have for questions, and they will reach out if you have any further questions. Thank you again to our presenters and all of our attendees for attending this webinar from Medical Design and Outsourcing, and a special thank you to our sponsor, Iconics. I hope you all have a good weekend. That's all we have.
All right, thank you, everyone.